So let's move forward, and now we will talk about turbines. So technically, a turbine is a device in which power is developed as a result of gas or liquid passing through a set of blades attached to a shaft free to rotate. Now this is kind of a definition for turbines. You should remember, I think I have shown you few examples in the last lecture, and now I can just give you an idea about the wind turbine. I hope you have seen it. Wind turbines, the large wind turbines in the European countries generally, you might have seen it on one of the departments out there. So what you can see is air is coming onto it, and those wings, those are known as blades. I told you that those are known as blades. Now that air, which is basically the liquid or the fluid, let's say any liquid or any fluid, so if air strikes with those blades, it transfers its energy, okay, and the shape of the blade is designed so that you can make them rotate by just a very small velocity of the air, okay. So what you can see is air strikes with the blades, as a result the blade starts rotating, and those blades are attached with a free shaft that basically runs a generator, and that's how you can convert that translational energy of or the kinetic energy of the air into the rotational energy of the blades, and then rotational energy of the shaft, and finally it would be converted into electrical energy by running by running a generator, okay. So that's how this turbine works. And most of the time those turbines are also used for hydropower. I hope you know that. You might have seen some installations, some small installations in small dams. You might have seen it, okay. So those turbines are basically hydropower turbines. You can also see few turbines being run by steam, okay, steam. So it depends on your output or on the available fuel, what kind of turbine you should use. And remember that the design of the blades, design of the passages to let the air or fluid pass through it, it depends on the requirement, it depends on the availability of the fuel, okay. So it is not basically random, everything is related to some design, and those designs are related to thermodynamics, fluid mechanics, then you may deal with structural vibrations, okay. So okay, one thing which is to be remembered during solution of the problems, if you are talking about a gas, you can have enthalpy not only from the thermodynamic table but also from that ideal gas law. I hope you remember that I think some properties can be found out from ideal gas law, and some properties can be found out by H equals Cp delta T, sorry, delta H equals Cp delta T and Cv delta T equals delta U. So you can use those relationships as well. Now let's talk about compressors and pumps. So in compressors and pumps, work is done on the substance flowing through them in order to change the state of the substance. And typically, how do you change the state? By increasing the pressure and or elevation. Okay, you might have seen those pumps installed in your homes, generally known as those donkey pumps, right? Commonly in market they call it like donkey pump. So what they do is they basically pull the water out of your underground water tank and they send it to the topmost tank, okay, on the roof of your house. So what they do is they are basically increasing the potential energy of the water by sending it to a higher level. Okay, so and if they are basically doing that, they need to suck it. They need to suck it. They need to generate that kind of pressure difference which can pull the water from the lowermost tank to the topmost tank, and then basically you do it by supplying electrical energy to it. Okay, remember you supply electrical energy to it. Basically you do some kind of work on the system. Just look at the definition. Work is done on the substance, and then finally it does that work on the water, and finally it is going to the top level. And there is one thing that whenever you talk about that compressor, you might be seeing the transportation of the gas in the circuit of a refrigerator. Okay, you might have heard about this compressor in the refrigerator, right, or in the air conditioner. So whenever you deal with a gas, transportation of a gas, you call it a compressor. You say that you are dealing with compressor. Okay, all the equipment dealing with the gas, they are basically compressors. And if you are dealing with liquids, you call those equipments as pumps. Okay. Gentlemen, before I move on, I would just show you few things about the heat exchangers. Just see those heat exchangers. I'm sorry for some kind of disturbance in that animation. I don't know. By the way, you might have seen that from inside the tube, there are two tubes, by the way. They are annular. Annular means one tube is basically within the other tube. Okay, and those two tubes are eccentric. They have the same center. So if you see that, by the way, it is just like that. Those pipes are just like that. Okay. So if you see that from the inner tube, you may have hot fluid, and from the outer tube, you may have cold fluid. Right? And once they pass through those tubes, they can exchange the energy. Energy can be transferred from the hotter fluid to the colder fluid. Okay. And there can be other things. These are, by the way, different types, and the equipment which is used for this kind of heat exchange, it is known as heat exchanger. Okay, you would see that heat exchanger in your cars as well. Have you seen those radiators in your cars? And then it is so interesting that sometimes you might have seen those just give me a minute. You might have seen those kind of structures on dinosaurs. Have you seen those on the back of the dinosaur? I mean, those kind of structures are there for heat exchange. Okay, these kind of structures, typically we call them fins. but remember that they help them exchange heat with the environment. Okay, and then what you can see is this is something which is about the heat exchanger which are newly developed. You can see that now see those passages. Now from the vertical passages you may have hotter fluid passing through it, and from the horizontal passages you may have colder fluid, right? And see how condensed they are. This is the internal structure of a heat exchanger. Okay, these are different types of heat exchangers, and this is the car radiator. I hope you can see it. Once you open the bonnet of your car, you can see those kind of structures. These are different types of it. It can have multiple inlets, multiple outlets, depends on the design. This is a typical working of heat exchanger in a power plant, or you can say this is known as shell and tube heat exchanger. If you see it, just see this pink fluid, it shows, I think, the hotter fluid, okay, and the blue one is the colder fluid. Once it passes through it, they basically exchange energy, okay. And you can increase the number of tubes into it. You can increase the number of tubes. You can design the passages depending on your requirements. What temperature do you need at the outlet of the colder fluid or at the outlet of the hotter fluid? Okay, it depends on and everything would be studied in your heat transfer course. And this is the last one which I wanted to show. Just see that this is the hotter fluid which is going there. So in one compartment you would see hotter fluid is there in every alternate compartment, and those empty compartments would be filled by that colder fluid. Okay, and due to the conductivity from those walls, they can exchange heat. Okay, so I just want to give you an idea what those heat exchangers are, and basically they have some relationships with all those principles which we are studying in the class. Okay, and everything can be transformed into a statement. Their design problem can be transformed into a statement, just like the examples given in your book or the numerical problems given in your book. Okay, you can convert those design problems into the statement, and then you can find out, for example, if this information is given and this is to be required, you just need to know what principles is the better one to find that information out of that statement. Okay, methodology remains the same. You know how to look at the thermodynamic tables. You know what is the first law of thermodynamics for this control volume based systems, which are basically the open systems. You see mass is going in, mass is going out. So you know the meaning of all the terms. So I hope you would be able to solve problems. I've also given you second assignment number 2. Okay, please solve that assignment, and the submission time is by the end of next week. Okay, gentlemen, I would solve this example from your book. By the way, this example is related to, again, cooling of some electrical equipment. So if you look at the cooling system for a computer, just treat this box as if you are dealing with your computer, and you can see some electronics is there, and there is a fan out there at one side, and then there would be an outlet. Okay, just read the problem, and then I would quickly tell you how to solve it. The electronic components of a computer are cooled by air flowing through a fan mounted at the inlet of the electronics enclosure. So see, we are going to apply that classroom knowledge or that theoretical knowledge on designing something which is there in real life. Okay, so at the inlet of the electronics enclosure, at steady state, air enters at 20 degrees centigrade and 1 atmosphere. Generally room air is at this temperature and at the same pressure. For noise control, the velocity of the entering air cannot exceed 1.3 meter per second. It means the maximum velocity which you can have at the fan or at the inlet, that can be 1.3 meter per second. For temperature control, the temperature of the air at the exit cannot exceed 20 degrees centigrade. right? So at the exit temperature is also given, it is 32 degrees centigrade. The electronic components and fan receive respectively 80 watts and 18 watts of the electrical power, right? So determine the smallest fan inlet area in centimeters square for which the limits on the entering air velocity and exit air temperature are met. So remember, they are giving you the maximum possible velocity of the air and maximum possible temperature of the outgoing air, okay, and they are asking you for the minimum area which is required to have those quantities, right? So let's talk about the governing principle. I mean, you know that this is a control volume. This whole body would be a control volume, right? Because this is what we are talking about. And then you can see air is coming in and it is going out. So it means what kind of system it is? It is control volume based system. And for control volume based systems, because we need to conserve energy, so that energy can be conserved by applying first law of thermodynamics over there mathematically, and we can assume that we are talking about steady state systems. We can assume that we are talking about, why? Because fluctuations are very small. We can just assume it. So left hand side is 0. Left hand side is 0, and if you remember, this was, and finally you would have what? M dot is it something which we had? So just see, by the way, there can be some heat transfer from the system to the surroundings, but if we look at this statement, we have not been given any kind of information about it, okay? So we can just assume that there is minimum heat transfer. And what about this control volume work? Do you remember? It includes shaft work, it includes some kind of displacement work, and it includes some kind of electrical effects as well. So this is something which is what? And because that work is being done on the system, so that would be negative finally. That would be negative, remember that. So, and if I ask you, this is H2 and this is H1, what about that? H2 and H1, how can you find it out? Air temperature is given at the inlet only. What about the outlet? Okay, for outlet it is also given, it cannot exceed 32 degrees centigrade. It cannot exceed 32 degrees centigrade, remember that. So, because it is, you can go to the property tables and then you can also use that law, Cp delta T. You can use that as well, okay? And then what about this one, V2 minus V1, is it given? V1 is given, okay, what about V2? Fan with what? No. Fan will make noise if the velocity exceeds at the inlet by 1.3 meter per second. Any idea how can we do that? Sorry. So see, if you even want to take this V1 equals V2, you would assume that the passage of the air inside that box is very small. I mean, if it enters from this side, and it has basically a very few, it has a very small distance to cover inside that compartment. So it would go outside, out of that compartment, I think with a very small decrement in its velocity. Okay, with a very small. So you can just assume V2 equals V1. So whenever you take some kind of assumption, you assume it logically. Okay. So I am just assuming that the box is very small, If it is coming in, it needs to cover a very small distance to go out of it. So, and what about that Z2 minus Z1? It would be 0. Why? Because those two points are at the same height. So finally you would get, generally it is very small. If you look at a personal computer, it's very small distance. And if it is not given, you can always write it at the top of your solution that you are assuming that the length is very small. Okay. So 0 equals minus W dot CV plus M dot H1 minus H2. And remember, this can be converted into M dot Cp T2 minus T1, and this would be minus W dot Cv equals 0. We also know that we can write this M dot as what? A1 V1 over this small v1. Okay. So this M dot can be replaced by its equivalent relationship from this one. Okay. So if you get the value of M dot from this relationship, put it over there, and then you are establishing some kind of equivalence between the area and the temperature at the outlet, okay, and the velocity at the inlet. So everything would be related then. So if, let me write down the final expression. This A1 would be equal to 1 over V1 minus W dot CV over Cp T2 minus T1 RT1 over P1. So why did I use this relationship? Come on. And it is used against what quantity? This one. Rho 1 V1 equals what? RT. Okay. So because this information is given to you, so instead of finding V1 from the thermodynamic tables, what you can see is you can always use that ideal gas because you are using it for air. So you know V1, you know T2, and you can have at least A1. But my point is, it said that V1 cannot exceed 1.3. So it means for this question, V1 needs to be less than 1.3 meter per second. And T2 needs to be less than 32 degrees centigrade. And you were asked about the minimum area. Minimum area. Now if you see that statement is putting a limit on the maximum value of those two quantities, maximum values, right? And if you look at this relationship, this V1 is inversely proportional to A1, isn't it? And similarly, this T2 is also kind of inversely proportional to A1. So at the maximum value, you would have minimum value of area. Okay, and if you look at that statement, that due to that maximum and minimum thing, they solve it as an inequality. Okay, they solve it as an inequality. Remember that. So my point is just to give you an idea that you use these relationships for the solution of practical problems. Don't treat those problems as if they are simple numerical problems, and read the statement very carefully because it also teaches you something about the engineering systems. Okay, thank you.